Last class we discussed about the quantum numbers that includes principal quantum number, asymptotal quantum number, and magnetic quantum number. I told you that these three have been derived from Schrodinger's wave equation. Let us discuss one more quantum number which is known as spin quantum number. Okay. Spin quantum number is not a part of Schrodinger's equation, but it would have the important application as the first three quantum numbers only give us an idea about what are the orbitals, what are the subshells, and what are the shells. But spin quantum number tells us about how the electrons are and how different two electrons can be. Okay. So what it meant is, imagine if there is an orbital here. Orbital is like some space or a shape. Let me take out a shape itself directly. Suppose this kind of shape is there, which has been made by electron cloud. Okay. So this cloud of electron often suggests that an electron which is present inside is either moving clockwise or clockwise here or anti-clockwise in the respective lobes. Correct? So spin quantum numbers suggest an electron within the orbital is either going to have a clockwise spin or an anti-clockwise spin of electron on its own axis. Got it? This is one way of explaining it. The other way is that electron, if you assume it like a wave, it is, imagine making some kind of a helical wavic form like this in a defined or a confined space. And the other one is making, the clockwise helical space like this. So one is designated as plus half, the other one, one is designated as plus half, the other one is designated as minus half. So clockwise is designated as plus half and anti-clockwise or counterclockwise is designated as minus half. This is a quantum number designated for that particular electron. Okay. So this is clockwise and this is counterclockwise. Counterclockwise. In simple terms, guys, imagine if you have n is equal to 2. Then what are the L values? You can have 0 and 1. And what are the ML values? ML values will be 0. When L is equal to 1, we learned that ML value will be minus 1, 0, and plus 1. Okay. So let me remind you, these are orbits, these are subshells, and these are orbitals. Got it? And then comes spin, which means every orbital possess or have an ability to accommodate two electrons in it. And each electron can have a particular spin. That includes plus half, and minus half, plus half and minus half, plus half and minus half, plus half and minus half. So you can see when it is n is equal to 2, that is in second shell, we have how many electrons? Maximum how many electrons we can accommodate? We can accommodate 1, 2, 3, 4, 5, 6, 7, 8. And we learned this. It is generally going to be 2n square. These many number of electrons we can accommodate. So here comes a very important term known as quantum set. Quantum set. Quantum set is a designation of quantum numbers, which includes n, l, ml, and ms. Okay, so n, l, ml, and ms. This one. So you see the quantum sets here. We have 2, 0, 0 plus half. 2, 0, 0 minus half. Then 2, 1, minus 1 plus half. 2, 1 minus 1 minus half. And 2, 0, sorry, 2, 1, 0 plus half. 2, 1, 0 minus half. 2, 1 plus 1 plus half. And 2, 1 plus 1 and minus half. These are the quantum sets. In short, this quantum set is like the address for an electron. Address of an electron. Okay. Every electron would have a particular address associated with it. So these are like the pin codes you can call, or some pin numbers of electrons, which tells us what is the exact position or what is its behavior, what type of orbital it is present in, what is the subshell it is present in, what is the orbit number it is present in. That is the information you will get using these numbers. Okay. So one thing to notice here is every electron has a different value. In some cases, the first three values may be same, but the last value is different. Got it? It's there. Got it? This is how you identify the address. Now, given given any quantum set, you should be able to figure out if that is correct or not. Notice one thing. Let me put it as a note. For every n value, we shall have, okay, we shall have 0 to n minus 1 L values, and minus 1 to plus 1 plus minus L to plus L ml values, and every ml has plus half and minus half spin value. That is what you need to understand. So please check this out quickly. Kapil, Kenneth, is that good, beta? Did you understand what I tried to say?
Yes, sir.
Done.
Yes, sir.
Okay. Now what I would do, I would give you a unique quantum sets. Using those sets, please try to figure out which of them is correct. Got it? Set number 1. Suppose I give you 6, O, O, and 1. 6, 6, 5 plus half. Okay. 4, 0, 1 minus half. 4, 2, 1 minus half. 3, 2, 2 minus 1. 3, 2, 0 minus half. 2, 1, 0 plus half. 5, 5, 5 plus half. 7, 0, 1 plus half. Okay. Now, if this is how the quantum sets are given, the follow-up is simple. Every quantum set follows from N to L to ML to MS. So for this particular quantum set, please check which one of them would be correct. Please check out which all cases are correct here. See, first one. When n is equal to 0, L values could be, n is equal to 6. L value could be 0, 1, 2, 3, 4, 5. Because n value will be from 0 to n minus 1. Hence, this one and this one is correct so far. And when L is equal to 0, M value will be 0. That is also correct. But spin value does not have anything other than plus half and minus half, which means this quantum set is wrong. Second, for n is equal to 6, L value could be 0, 1, 2, 3, 4, 5. But I have given 6. So that is clearly wrong. Okay. Clear? Next. Third one, when n is equal to 4, L is equal to 0, M cannot be 1. Because for L is equal to 0, ML has to be 0. So that is also wrong. Fourth one, when n is equal to 4, then L will be equal to 2. That is okay. And M can also be equal to 1 because ML values changes from -2, -1, 0, +1 and +2. These are all the possible values. So of course here we have it. So that means this is a correct set. Next, 3, 2, 2, 1. When it is 3, 2 is possible, 0, 1, 2. This 2 is possible, but not -1. So this is again an incorrect set. When this is 3, 2, 0, minus half, that is possible. So that is correct. 2, 1, 0 plus half, that is also correct. That is all possible way. Seventh, when n is 5, L can never be 5. So that is wrong. When L is 0, M can never be 1. So that is also wrong. Okay. So only these three are correct. That's right, Dave. Okay. So fourth, fifth, and sixth are the correct way of representations. So this completes the quantum set. How to figure out what are the quantum numbers for various electrons. Okay. Now, how do we assign these quantum numbers and how many number of electrons can be stored in every orbit, orbital, and how many will be in subshell? That information we will get to know as you start filling electrons. So how to fill the electrons or distribution of electrons in the respective subshells and orbitals? It depends upon what is the energy of every orbital. Okay, what is the energy of every orbital and subshells? See, to figure out that, where do we place the electrons? We follow three rules: Aufbau's rule, building up rule, Hund's rule, symmetry rule, Pauli's exclusion principle. That means exclusivity rule. What is that? What are these one by one? Let's see. Aufbau's rule suggests that electronic distribution is based on increasing order of the energy of subshell. Okay, which means every subshell will be completely filled first as long as it has lower energy. Then it will go to the next subshell which is slightly higher energy. So progressively, as the energy starts increasing for a subshell, we have to complete filling of one subshell and then go to the next subshell. Got it? How do we decide that which subshell is lower energy or which subshell is higher energy? Okay, this can be based on N plus L rule. N plus L rule. That is, if the N plus L value is lower, then lower is its energy. So that subshell will be at lower energy. Next, if N plus L value of the subshell is same, if I'm adding N plus L value, you got same, then the one which has the lower N value has the lower energy. So follow very simple rules here. N plus L rule is based on lower sum. Lower the sum, lower is the energy, and that orbital or that subshell has to be filled first. Got it? So now notice, for n is equal to 1, the subshell will be 1s. For n is equal to 2, there are two subshells. One is 2s and 2p. 2s designates to azimuthal quantum number 0, and here azimuthal quantum number is 1. Okay. So n is equal to 3, we will have three subshells, 3s, 3p, 3d. N is equal to 4, we will have 4s, 4p, 4d, 4f. N is equal to 5, we will have 5s, 5p, 5d, 5f, and 5g. So every time you go to the new shell, you'll always have an increased subshell also. Now notice n plus L value. So n value is 1, L value which is based on s orbit. So that is, S subshell. S subshell's value of L is 0. So 1 plus 0 is 1. Next, n is equal to 2. We have 2 plus 0, that is 2. And 2 plus 1, that is 3. Because the L value for p orbital is, p subshell is 1. So when n is equal to 3, we have 3 plus 0, 3 plus 1, 3 plus 2. When n is equal to 4, 4 plus 0, 4 plus 1, 4 plus 2, 4 plus 3. N is equal to y, similarly, it will follow. Now go one by one here. N is equal to 1, this has the lowest energy. Okay. Then 2s, correct? Like this. You can see then 2s, then 2p, then 3s, then 3p. Okay. Then we have 4s, then we have 3d. It is not directly going to 4p. You can check it out based on the n value. Why? 4 plus 0 here and 3 plus 2 here. So 4 plus 0 is lesser value. So therefore, this has to be filled first. 4s has to be filled first. Then only it will go to 3d. And from 3d it will go to 3p. 4p, sorry. From 4p it will go again to 5s. Why? 4 plus 1 is 5. 5 plus 0 is also 5. But which has a lower n value? 4p has the lower n value. Okay. And after 5s, again you'll get to 4d. From 4d, you'll get the 5p. From 5p, you'll get the 6s. From 6s, you'll go directly to 4f now. Okay. 6s is 6 plus 0. 4f is 4 plus 3. So which is 7. And then comes 5p, 5d. Okay. And that will continue here as 6p. And then we have 7s. So if I put all of them together in the increasing order of energy, then I will get 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5f, 6s, and 4f. This is the order in which you have to fill the electrons. Now, let me tell you, suppose if it comes to 2p, when it comes to s orbital, the subshell and orbital is only 1. So that means you will only have one orbital here. Here also we have only one orbital. But when it comes to 2p, 2p will have three orbitals, because when you have 2p, you have three different magnetic orientations: -1, 0, and +1. So if one is -1, the other one is 0, then the one is +1. So these blocks in a way represent that how many number of orbitals they have. So 2p has 3 orbitals, 3p has 3 orbitals, 3d has 5 orbitals, 4p also has 3 orbitals, 4d also has 5 orbitals, and so on. So you keep filling them before you go to the higher orbit. So let me show you with some examples here. If we have nitrogen 7, see if you already have my notes, pre-notes, please start writing in that. Otherwise, put it in the rough work. That is, if n is equal to 7, how do we fill the electrons? You know that 1s is an orbital which has a capacity of 2 electrons. 2s also have 2 electron capacity. Now when it comes to 2p, there are 3 orbitals, 2px, 2py and 2pz. So if each orbital can carry maximum of 2 electrons, so a p orbital can carry maximum of 6 electrons. So let me put that in here. Max electrons, max electrons that can be accommodated in subshells. S is 2, P is 6, D is 10, F is 14. Why? S has 1 orbital, P has 3 orbital, D has 5 orbital, F has 7 orbital. See the pattern? 1, 3, 5, 7, 9, 11, and so on. This is how the pattern goes. And each orbital can have 2 electrons each. So multiply that with 2. So that makes it 2, 6, 10, 14, 18, 22, and so on. This is the way the number of electrons will be filled. All right, just a second. One is 2, 2 is 2, and 4 electrons have already been done. So write 3 more electrons here. So that makes it 2p3. All right. Next, potassium 19. So first we will fill 1s, then we'll fill 2s completely, then we'll fill 2p also, 6. So total 10 electrons done, 3s 2, 12 electrons done, and 3p 6, 18 electrons done, and then 4s we can, because now we have only one electron left, that is the electron we will put through. Got it? Next, calcium 20. So 1 is 2, same thing, 1 is 2, 2 is 2, 2p6, 3 is 2, 3p6, and 4 is 2. 36. Here we have 1 is 2, 2 is 2, 2p6, 3 is 2, 3p6, 4 is 2. Correct? Up to this, we have how many electrons? Check it out. 10 here and 10 here. Correct? 10, 10, 20. Then 3d 10, 30. And then 4p6, 36. Clear? This is the sequence in which you have to go. If you're not able to recall, please write down the sequence once, everybody. One is, at least you should learn up to 4f. This is how much you are expected to know, how the filling has to be done. Finished? What is iron? It is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d6. Because up to this, we know that 20 electrons are being done. So rest of the 6 we can accommodate in 3D. This is the way we write the configuration. Got it? Now let me remind you, there is in the periodic table, anyways, we'll be learning in detail, but just for the reference I'm giving you, group 18 means noble gases or inert gases. Inert gases. Okay. Inert gases starts from helium. Helium, neon, argon, krypton, xenon, and radon. Okay. Check out what are their atomic numbers. Helium has 2 electrons, or I would say 2 protons. Neon 10, and you keep adding 8 again. So 18. From here you add 18. So you'll add 36. 36 plus 18, 54. Then you add 32, which makes it 86. So these are their atomic numbers: 2, 10, 18, 36, 54, 86. These are the respective atomic numbers. Correct? Now, what we usually do, sometimes if this configuration becomes longer and difficult to remember, we will try to remember these numbers. Now, for example, 7. 7 is more closer to this one, 2. Check out the lowest number, which is closest. So, lowest number closest is 2 here. So, the same configuration can also be written as helium 2s2 and 2p3. So instead of writing 1s2, I can show that I filled up to the helium number of electrons, and then we have to fill the rest of them. Similarly, in this case, 19 is pretty close to 18 now. That is the lowest number which you can think of. So here we can simply write it as argon 4s1. That's it. Because up to 3p6, it is covered as argon. So here also we can write it as argon 4s2. And next here 36. 36 is exactly krypton. So okay. So now you could do it in both ways. Okay. Normally, sir, do we simply write as krypton? Well, this is not the way to write. So usually inert gases we do not write it, but to just write it, you should always write the previous one. So argon up to 36 it is done. Then so then up to 3p6 we know that it is argon. So then we have 4s2, 3d10, and 4p6. This is another way of writing. Next one, 26. 26 means again I have argon, then 4s2, 3d6. This is the way we write. Everybody understood? So this is the abbreviated form of writing out what are the uh, electronic configurations. But if you notice, this is only based on first rule. And what is the first rule suggesting? That is, you have to fill the electrons in subshells completely based on their progressive increasing energy order. Got it? Any doubt here, guys?
No, sir.
Everybody understood, right? Good.
Sir, can I write that group 18?
Sure. Which one?
Group 18, inert gases.
Yeah, write down.
None, sir. Thank you,
Good.
sir.
Next, check out second one, Hund's rule of spin multiplicity. Okay, Hund's rule suggests that if at all we have degenerate orbitals, what are degenerate? That means these are orbitals having same energy. Okay, for example, 2p. 2p is a subshell, but within that subshell, we know that it can have three different orbitals, three different orientations. One is 2px, 2py, and 2pz. And each of these orbitals have same n plus l value and also same n value, which means as per Aufbau's rule, all these three orbitals have same energy. So this 2px, 2py, 2pz have same energy. Hence, we call them as degenerate orbitals. So these three are called as degenerate orbitals. Now, here is an important catch. While filling the electrons to degenerate orbitals, we have to fill at least one electron of the same spin to each and every orbital. Okay, so it's not like we have to fill one orbital completely and then go to the next one. Since energy of all the orbitals is same, you have to give the preference equally to all of them. Okay, so if you give the equal preference, then how do we write down that? Check out. For example, nitrogen, we just wrote this as 1s2, 2s2, and 2p3. Okay, now let me show the block representation. Block representation means this way. Okay, square boxes. So the first orbital is 1s2, second orbital is 2s2. Third subshell has three orbitals of equal energy. Because they have equal energy, I have fused those boxes. So now I have this as 2p3. So now notice this one. As per Aufbau's rule, first fill this one, then fill this one. But now the next three we have to fill it in these three boxes. Now Hund's rule is applicable. According to Hund's rule, you cannot give priority to one box over the other. You have to give all three equal priority, which means you have to fill one electron here, then the next electron here, then the next electron here. Got it? So if you're following that, then we say we are following Hund's rule. Got it?
Sir,
Yes.
can you explain one more time, sir?
Okay. You may have understood the point that 2px, 2py, and 2pz are degenerate. Correct?
No, sir.
Degenerate means they have same energy.
Oh,
Since they have same energy, when the electrons come, when the time comes to fill the electrons, like in this case, nitrogen, we have 1s2, 2s2, and 3 electrons are left over, which has to be filled in 2p. Since 2px, 2py, 2pz, all of them have same energy, so each box represent one orbital, 2px, 2py, 2pz. So instead of filling electrons only into one box, and you know that one box can maximum accommodate two electrons. One box is nothing but one orbital. Okay. So this orbital can maximum take two electrons, but I'm not giving two electrons directly. First, I will make an equal distribution as much as possible with every orbital. So you have to fill each orbital with one electron. And one more important task we need to check out is that their behavior should also be same. That means if one is clockwise, the other has to be clockwise. Correct? Then we say we are following Hund's rule. Yes, Dave, any doubt there?
no, sir.
Right. Now imagine what if at all I have to fill oxygen. Oxygen is 8 electrons. So which is 1s2, 2s2, and 2p4. So now as a block, I will write 1s2, 2s2, and then this block of 3 as 2p4. So it is 1, 2, 3, and then we have 4. Now see why we have to put it this way, correct? Because first I have distributed the first 3 electrons equally, and now the fourth electron has to come and change the spin, because same orbital cannot have two spins. I mean two same spins, because electron, if one electron is already making a clockwise rotation on its own axis, the other electron, when it enters in that space, it has to be always in an anti-clockwise direction. Got it? This is the way to represent. Now this OR, see this OR part carefully. I can write like this also. I have 1, 2, 3, 4 I can start here. Or I can write it as 1, 2, 3, 4 I can start here. Correct? Because it's not necessary that which box you are starting. It is essential that every time you fill the box, you can take any sequence. Like I can start 1 here, 2 here, 3 here, and make 4 here. That is still fine. I can start 1 here, 2 here, 3 here, 4 here. Or I can start 1 here, 2 here, 3 here, 4 here. Doesn't make any difference. In any way you fill it, correct? But the first 3 electrons has to be each one of them getting each one orbital getting 1 electron each. Okay. Is this part clear? Let me do the same thing for iron. Iron up to argon, all of them are completely filled. So I'm not writing anything about argon. Then we have 4s2 and 3d6. So you only write the boxes where you have electrons incomplete. So 1, 2, 3, 4, 5. So up to argon, all the orbitals have been completely filled with electrons. Now comes 4s2. 4s2 means 2 electrons here. Then see 6. 6 electron distribution. How would I go? Electron number 1, number 2, number 3, number 4, number 5. And then I will write it as 6. So that 6 can be written anywhere. That does not make any problem. So to be precise, this is 1, 2, 3, 4, 5, and 6th electron. Clear? So when we are able to give such kind of a distribution to every orbital, correct? So then we say we are following Hund's rule. I hope that is clear, everybody. Okay. Now listen, sir, is it always has to be clockwise? Not necessary. It is never said that clockwise has to be first and anti-clockwise has to be next. What I'm trying to say is that, see, I could have started like this also. First anti-clockwise, then clockwise. Okay. So that means like this, anti-clockwise here and clockwise here. I can write this way also. There is no problem. But a convention is followed that, let's say, an anti-clockwise is written anti-clockwise is written like this. Then this will be the clockwise form. Now let us start putting all anti-clockwise first. 1, 2, 3, 4, 5, and then comes 6. So this is also correct representation. There is no problem here. So it is not necessary that you only have to do clockwise first and anti-clockwise next. So this electron filling, I'm using it as a clockwise electron. And this symbol, I'm using it for counterclockwise electron distribution or electron representation. Guys, I hope you understood this part. If you are doing this, we say we are following Hund's rule. Next, Pauli's exclusion principle. See, according to Pauli's exclusion principle, No two electrons will ever have the same quantum sets, which we have done it earlier already. Because we always see that the quantum set is a unique number. Okay, it's like the UID, like an Aadhaar card for electron. So that number is fixed for that particular electron only. It cannot be mimicked with others. Yeah, we might have all three quantum numbers same, but at least one quantum number will be different. So that makes every electron unique. For example, helium we have four. Okay, four electrons. So configuration is 1s2, 2s2. 1s has two electrons, 2s has two electrons. Now, how do we write the quantum set? Check out this quantum set here. These are the serial numbers. So the first electron has n value 1, 0, 0 plus half. Second electron has 1, 0, 0 minus half. Third electron has 2, 0, 0 plus half. Fourth electron has 2, 0, 0 minus half. Okay. Sorry. So these are the four electrons present in helium. Notice carefully, none of these complete set is same for any other electron also. Okay. Clear everyone? Right. Now check this out. If a distribution is already given like this, 2s, 2p has been distributed. I want you to just pick out and tell me which of these are being violated and which of them are correct. Is it following those rules or not? Let me start with one. First one, there is only one electron added to 2s and directly we went to 2p. That is wrong, right? That's not how the off-Bose work. So off-Bose is not followed here. According to off-Bose, the lower energy has to be completely filled, then only we will enter into the higher energy. Second, is it following Hund's rule? See, Hund's rule is applicable for 2p because 2p has degenerate orbital set. So first electron was filled like this, second is filled like this, but third is supposed to be filled like this, but they have filled in a opposite spin. So that is also not following Hund's rule. Are we following Pauli's exclusion principle? See, for example, 2s. 2s 2s will have 2, 0, 0, maybe plus half. This is the quantum set for the first electron here. Now check out the second electron here. This one. This could be 2, 1, minus 1 and plus half. Correct? Now check out the third one. This third electron here. Third electron will be 2, 1, 0 and plus half. Now notice the fourth electron. This fourth electron may be 2, 1, 1 and minus half. Check this. All four have different values. That means it is following Pauli's exclusion principle. Now the simple way to judge whether the Pauli's exclusion principle is valid or not, you just need to do one thing. Check out, is there any box, single box, which has two electrons with the same spin? In that case, here both have same quantum numbers. Both have same quantum set. Got it? Now in this case, we can say both have same quantum set. As long as we are not able to see anything like this, then we say that the Pauli's exclusion principle is followed. Okay. So notice this one, next one. Here you can see Aufbau is followed. According to Aufbau, you have to just fill it. So it is filled. Now, Hund's rule. Hund's rule, as much as this degenerate orbitals are concerned, it is properly filled. There are two electrons. If there are only two electrons, I have to put it like this only. So there is no problem here also. Hund's is followed. But when it comes to Pauli's exclusion principle, notice this one. Both have same spin in the same box. That means it is not following Pauli's exclusion principle. Okay. Similarly, if you notice 2s and 2p here, so first case, we can see off both is followed because we have filled the 2 electrons and then only entered into 2p. And in 2p, I have used 2 anti-clockwise spins. So that is no problem as long as you are not putting both of them in the same box. That is correct only. Pauli's is also being followed in this case. So no problem here because you don't see that any one box has 2 electrons of same spin. Next here, off both is followed. Hans, check out. First, second, third, up to this Hans is followed. Then fourth has to be in the opposite spin like this. But here fourth is not. So which means it is not following Hans. Subsequently, because it is not following Hans, in a degenerate, it is not following Pauli's. Because this orbital now will have 2 electrons of the same spin. Okay, next. Check out in this case. Off both is not followed. Hans is followed. Why? I can start like this 1, 2, 3, and fourth one I can start it here. It does not make any difference wherever you start. So Hans is followed and Pauli's is also followed. Next case, off both is followed, Hans is followed, and Pauli's is also followed. Last case, off both is not followed, Hans is also not followed, Pauli's is also not followed. Okay. Please go through these examples with the distribution of electron, everybody. If you have any doubt, you can ask me now. I'll give a minute's time, go through. Fe plus 3 has electronic configuration like this. Argon, 4s2, 3d6. Okay. Up to Argon, we know that all the electrons are been completely filled. So I'm only writing the boxes for 4s and 3d. So 4s is only single box. 3d is 5 boxes because it has 5 orbitals. Right. Sorry. It has 5 orbitals like this. Now, following off Bose rule, we have 2 electrons here. Correct. Right. I'm writing first for iron. Okay. Iron is 26. Correct. So for iron 26, we have 4s2. Then we have 3d6. This is how the electrons are distributed. Now imagine I have given the charge as plus 3 here. The plus 3 represent that there is loss of 3 electrons. Correct? So when mxn is represented, n represent loss of n electrons. If it is given m minus p, that means here gain of p electrons here, p number of electrons. So there is a loss of 3 electrons. Well, that means I have to remove those 3 electrons from this body. Electrons will always be removed most easily from the outermost orbit. Now here up to argon we have 3p6. Then 3 number is also an inner orbit. 4 is an outer orbit. So from outer orbit you have to remove them first. So you will remove these two first. First you will remove this and then you will remove 1 electron here second. That will be the next electron you have to remove. Correct. So after doing that, what will become to Fe plus 3 now? Fe plus 3 will become argon. So this is not Fe plus 3, only Fe. Now Fe plus 3 will become 4s0 and 3d5. So total 3 electrons have been lost. Correct. Clear? So check out. Okay. Remove electrons from outermost orbit first. Outermost orbit first. Okay. So then becomes 4s0 and 3d5. Now you redistribute the electrons once again. Okay. So you see 4s we have 0 electrons and then we have 3d. So in 3d how many electrons we have? Check out. 5 electrons. So 1, 2, 3, 4, 5, following Hund's rule. Correct? Now you notice that when you have 5 electrons here, we say that we have 5 unpaired electrons. We have 5 unpaired electrons. So this data of how many unpaired electrons becomes very essential for us. Correct? So Fe plus 3 has 5 unpaired electrons. Okay? So unpaired electrons means only single electron is present in that particular orbit. So I can say that Fe has 4 unpaired electrons, while Fe plus 3 has 5 unpaired electrons. It has 5 unpaired electrons. All good? This becomes a very important application. That is, this data of unpaired electrons becomes a very important application. What are all the applications? You check out those parameters. There are mainly 4 parameters that we will discuss from now. First parameter is called spin moment or spin only moment or magnetic moment. All of them are one and the same. Okay. So in questions, if spin moment is the wording used, spin only moment or magnetic moment, all of them are one and the same. So it is how much amount of movement that is caused by the unpaired electron in the species. Let me tell you what it meant. Okay. Suppose when we consider electron is a charged particle. Okay. Any charged particle will always have a field around it. Because a charged particle acts more like a magnet, so it will establish a field around it. Correct? Now, usually what happens is like this. See, if suppose electron is here, one electron is here like this. So this electron will have a field like this around it, like a magnet here. Correct? This is like a magnetic field like this. Okay. Now, if I bring one more electron of a same kind here and place it here, correct? And imagine this. If the field electron field is going like this, correct? Let's say we write this is for clockwise kind of an electron. If I put one more electron here, which is an anti-clockwise one, that means the field will be in the reverse direction here, like this, like this, like this. Now, problem what happens is if they are close to each other in an orbit, so this is what happens. When I bring this electron, you can see one field line is always cancelling the other field line, which means if you take any particular vector here, like for example, the field vector is going this way, and for the same direction, the field vector is going here. So you can see what will be the vector sum of these two. That will be 0 because they are opposite to each other. That's the reason why whenever there is an electron field present, the minute it start pairing with the other electron, the entire field will get nullified. Okay, so it's so-called magnetic field around it will not be, we will not be able to feel anything in front of the pair of electrons. Got it? Because their fields are getting cancelled with each other. Okay. But what if there is only single electron? Imagine if this electron is not there. Then, if at all there is one more particle or some particle coming in the field lines of electron. So what happens? The minute we bring something to it, suddenly it might change the path. It might go away from it. It might be thrown away or it might be attracted. Correct? Something will happen. This virtual push, a virtual force which is acting on an incoming particle or any species, that is called as movement. Okay, and it is the spin of the electron which is causing that movement. Everybody clear on that? That's why we are only interested in unpaired electrons. More the number of unpaired electrons, more is the movement created. Okay, and that is called as magnetic moment. Okay, So see this example. So total number of unpaired electrons in the species, for example, nitrogen is 3. So there are 3 unpaired electrons. Number of unpaired electrons are 3. Okay. Since it is 3 unpaired electrons, how do we calculate mu? Mu is about spin moment or magnetic moment. So this is a formula that you will apply. That is root of n into n plus 2 Bohr magnetons. Right. So please remember this formula. This is a formula we'll be using quite often. That what is uh, spin magnetic moment here. So it is root of n into n plus 2. What is n exactly representing? N is the number of unpaired electrons. So check, when unpaired electrons are 2, so it will be under root of, sorry, we have 3 unpaired electrons. So 3 into 3 plus 2. So that makes it root 15 Bohr magnetons. So root 15 Bohr magnetons is a greater than 0 value. Correct? Now notice one important property. If any species, any atom or any ion, positive ion, negative ion or a neutral atom, anything, if you check out their mu value and found that the mu value is greater than 0, which means definitely that particular species will have at least one unpaired electron. Okay, then such a kind of species which have at least one unpaired electron are called as paramagnetic species. They are called as paramagnetic species. Check, any species which have unpaired electron, or if mu is greater than 0, these are called as paramagnetic species. Okay, and check now. Nitrogen, iron, chromium, potassium, all of them will have at least one electron present in them which is unpaired. Okay, so as long as there is an unpaired electron present, we say these are all paramagnetic species. When it comes to ions also, for example, Fe plus 3, cobalt, chromium plus 3, cobalt plus 2, copper 2 plus, right? And titanium plus 3, correct? Manganese plus 2. All of these all will have at least one unpaired electron. So that makes them as paramagnetic species. What do you mean by paramagnetic, everybody? Any species which is weakly getting attracted to the magnetic field. For example, if I take chromium or potassium near a magnet, okay, then what happens? That particle near a magnet as inside their field lines. Then what happens? The field lines will get redistributed and you will see the outward lines will be more, the inward light will be less. How many number of field lines are passing through a unit area? That is called as flux, magnetic flux. So you can see the flux is more on the outward and flux is less on the inward. So what happens? A natural push will occur. So that makes it to get attracted to the magnet. So these species, all of these species which I have written, they are all good paramagnetic species because they have at least one unpaired electron. All good, everybody? Next, diamagnetic species. That means any species which has mu value, that is spin magnetic moment, is 0. Then we say they are diamagnetic species. They are diamagnetic species. For example, if you take helium, argon, krypton, neon, calcium, all of them do not have any unpaired electron. Check out for calcium, no unpaired electron. Now, in the form of ions, if you notice, scandium plus 3, copper plus, zinc 2 plus, cadmium 2 plus, got it? Or in case of minus, N3 minus, O2 minus, got it? Sodium plus, right? And aluminum plus 3, right? Fluorine minus, chlorine minus, like this. if you notice all of these positive, negative, and neutral species, they all are diamagnetic because none of these elements or species will have any unpaired electrons. All right. So, magnetically speaking, what we are trying to help out is like this. If there is a material brought into magnetic field, the field lines will change, redistribute themselves such a way that the inside flux is more compared to outside flux. So naturally, the particle will be thrown away from the field. So that's why they usually get repelled by the magnet. So diamagnetic will always try to get repelled from the magnet, weakly repelling from the magnet. Please go through it once quickly. If you have any doubt understanding magnetic movement, please let me know.
Sir, is there any way to identify whether it is
Any doubt here, everybody? Okay. So now notice this case. Manganese 25. When it comes to manganese 25, this is the configuration. Up to this is argon, right? So that is argon, and then 4s2 and 3d5. So notice this one, 4s2, 3d5 means 4s will have 2 electrons, 3d will have 5 electrons. And all the 5 are unpaired electrons. So you can see under root of 5 into 5 plus 2. So that makes it root 35 Bohr magnetos, which is greater than 0. So which means it is sufficiently paramagnetic in nature. All right. While cobalt 27 will have up to 36, it is argon 4s2 3d7. So 3d7, while you distribute following the Hund's rule, you'll get 1, 2, 3, 4, 5, 6, 7. So how many unpaired electrons left? 3 unpaired electrons left. So because we have 3 unpaired electrons, this is the magnetic moment calculation, and naturally it is paramagnetic because mu is greater than 0. So I hope you guys understood this point. Okay. Right. Now, why don't we try this one now? Try out. Let's see the tryouts here. First species is bromine minus. Okay. This is how it is written. Okay. Second, got it? Cr plus 3. Third, okay. Cr plus 3, not Cr plus 3, sorry, cobalt plus 3. Okay. Then nickel plus 2. Fourth one, we have uh, iron plus 3, we have done it already, sorry. So what we can do, scandium, vanadium. Okay. Vanadium plus 2 plus 3, vanadium plus 3. Atomic number of vanadium is 23. All right. Atomic number of nickel is 28. Cobalt is 27. Okay. So now let's try to put the configuration and see how we can get this. So bromine is supposed to be 35. 35 is its configuration. Okay. 35 means the closest number is still argon. So we have argon, correct? Then we have 4s, sorry, 5s2. Okay. Okay. No, this is in 4s only, right? After this we have 4s2, so that makes it 20. Then 3d10, which makes it 20 plus 10, 30. So then 4p5. So this is a configuration, correct? Out of these, which is the outermost orbit? Which is the outermost orbit? Orbit is fourth orbit. So electron has to be removed from this. Now within 4p, 4s and 4p, correct? Either to remove the electrons or to add the electrons, you should always use p first. Okay. So within ns, NP, ND, NF. Either to remove the electron or to add the electron. This is the sequence we need to follow. To remove the electron or to add the electron. So now we have minus sign. Minus sign means one extra electron. Within this, we have one extra electron. So that means one electron has been added. So on adding that electron, what do we get? Now this configuration will become 4p6. Okay, so that will now become 4p6. Since it has become 4p6, which is same as that of krypton now. It has become same as krypton. And since krypton does not have any unpaired electron, so mu will be 0. Hence Br minus is diamagnetic. So Br minus will remain diamagnetic. Okay. And cobalt plus 3. Cobalt plus 3, it is argon 4s2 and 3d7. This is the original configuration. I have to remove 3 of them. So first we'll remove out from 4s, then one from d. So that makes it 4s0 and 3d6. Okay. So now if I write the block forms here, Rs, argon 4s0, and then we have 3d. We have 3d. So we have 6 electrons here, 1, 2, 3, 4, 5, 6. This is the way we distribute. Now you can notice that the number of unpaired electrons are actually 4. So which means the mu value is under root of 4 into 4 plus 2, which is root 24 Bohr magnetons. And since mu is greater than 0, so it is a paramagnetic species. It's a paramagnetic species. Okay, so please check this out. This is how you need to solve it. Nice. So when it comes to nickel plus 2, this will have a very similar configuration. So that is going to be 4s0 and 3d8 because it is supposed to be 28. Out of 28, 2 electrons have been removed. So 4s is the outermost one. So we have to remove those electrons first from 4s. And as we done that, now if I distribute these electrons, this is argon, 4s is empty. Then in the case of 3d, we have 1, 2, 3, 4, 5, 6, 7, 8. So you can clearly notice that the number of unpaired electrons are 2. So there are only 2 unpaired electrons. So number of unpaired electrons are 2. And mu will be equal to under root of 2 into 2 plus 2. Correct. So that is equal to root 8 Bohr magnetons. And that is still greater than 0, which makes it paramagnetic. This still makes it paramagnetic. Okay. All good, everyone?
Yes, sir.
Right. Kapil, any doubt here?
No, sir.
Manav?
No, sir, no, no.
Right. Now notice the special cases. That is, in case of chromium and in case of copper, how is the configuration different? The expected electronic configuration is this one. 24. We have 1s2, 2s2, 2p6, 3s2, 3p6. 18 electrons done. 18 plus 2, 20 done. Then 4 electrons. This is the expected configuration. Or we can simply write it as argon 4s2 and 3d4, which means we have no unpaired electrons here, but you will have 4 unpaired electrons here. This is the way the configuration is supposed to be. But in reality, the electronic configuration is like this. Argon 4s1 and 3d5. So this way, now 4s will have 1 electron and 3d will have now 5 electrons. 1, 2, 3, 4, 5. Got it? Now, here is something interesting, everybody. Please check. When it comes to 3d orbitals, there are 4 electrons present in it. Since all of them have equal amount of energy, these electrons can freely go to this orbit, while this electron can come into this orbit. It's like in your house, you have various doors, right? Correct? So now imagine if all the doors are open. If all the doors are open, you don't have to do some extra work of opening the door or going to the other room with some different energy. No, right? From one room, as you go to the other room, you will walk simply with the same amount of energy, probably carrying the same amount of energy in both the scenarios. Which means there is a chance that electrons can always keep pushing each other, right, to exchange themselves. That is, one electron as it comes here, this electron can go here. Correct? This is called one unique exchange. Similarly, this electron can actually make an exchange with the neighbor here also, like this. And this electron can make an exchange here also. This can make an exchange with that. Correct? So this way, if you calculate all the possible number of uh, unique number of exchanges, how many exchanges we can have here. So you would notice this one here. Between these two, one exchange, one exchange, one exchange. Between these two, one exchange. Between these two, other exchange. And here you have other exchange. So total number of exchanges possible in this case are 6. Okay. So you can see 6 different unique exchanges we can make. This is the basic permutations. You know that there are 4 different positions. Then how many different exchanges we can make? 4C2. Likewise, here, if you notice, in this case, we can have one exchange between these two, one exchange between these two, one between these two, one between these two. And then again, we can have exchange between these two, between these two, and between these two. And we can have exchange between these two, and lastly, we can have exchange between these two also. So if I count all of them, we are getting it as 10. 10 different exchanges are possible. Correct? Now see the importance what has happened. Earlier, in the ground configuration, expected configuration, we have 6 exchanges possible. But now, if I take this type of electronic configuration where off-Bose rule is violated, then I'm actually getting 10 different exchanges. Now hear it out. If you have more number of exchanges, the molecule or the compound or the atom will remain more stable. It will always remain more stable. Now, why is that so? See, more the number of exchanges we have, correct? More amount of energy can be thrown out. Reason being, whenever electron tries to pair, a pairing requires an energy because both of them are negative charges. So we have to take some energy and put it there. But when they are separating out and they are trying to occupy more space, then the repulsions will decrease. When the repulsions will decrease, energy will automatically come out of the atom and it will become more and more stable. So more the area covered, correct? More the amount of area or the surface covered, more is the amount of stability you will attain. That's why chromium, instead of being in an expected configuration, it will now change to a more stable configuration, which is 4s1 and 3d5. So, sir, is there any particular amount of exchanges only then we violate the oppose rule? Yes. So, if you have at least this 4 unit difference, then the exchanges are possible. The difference in the number of exchanges will be 4. Then it is definitely possible. Okay. So, you can see due to the high exchange value, 4s1 and 3d5 is the ground state configuration for chromium. Okay. The similar thing runs in the case of copper also. Okay. Copper expected configuration is 4s2 and 3d9. So when it comes to 4s2 here, we have 2 electrons. 3d9 here, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now listen up. When it comes to exchanges, exchanges will always between the two set of same spin orbitals. Correct? See, what I'm trying to say is imagine when you go from one room to other room. Okay, clear? When you jump into the other room, it is not like the gravity is reversed or you suddenly got tilted. Still, the way you are walking, the spin, the orientation, how you are, it will continue, right? That's the same thing happening here also. When electrons exchange, it's not like after exchanging their spin will change. No, then it is not an actual exchange. So when we call something as an exchange energy, we are expecting that same spin, same behavior is still carried forward. Hence, in this case, you notice when you have 4s1 and then we have 3d9, 1, 2, 3, 4. Now this will become 3d10. So we have all 10 electrons. So check out how many exchanges were originally present. See, all the clockwise one, we know that we have 10 exchanges. All the anti-clockwise one, we get 6 exchanges. That we have learned it, right? When you have 4 electrons, we will get 6 exchanges. When you have 5 electrons, we will get 10 exchanges. So that means total of 16 exchanges we will have. But when you have all the d orbital filled, then you'll have 10 plus 10 total 20. So 20 exchanges are possible. Now again check out how much is the difference in the exchange energy. 4 units of difference. So 4 exchanges will always overpower this energy required for one electron to go here. Hence, this is a better configuration, 4s1 and 3d10. Clear, beta? So I hope you guys understood why chromium and copper would have exceptional configuration this way. All good? Please check.
So, sir, for every other element, the exchanges are less.
Hmm?
For every other element, if the exchanges are less if they are changed.
Yeah, see, if the elements have a difference in the exchanges as 4, then that excitation is possible. Okay. If that much difference is not coming, then there is no exchanges happening. Clear?
Yes.
Huh? Everybody clear on that?